Welcome to exponential functions. Previously we studied trigonometric functions such as sine and cosine. We also looked at algebraic functions like linear, polynomial, and rational functions. In this chapter we will learn about transcendental functions. The transcendental functions are exponential functions and logarithmic functions. Take a minute and, using your graphing calculator, look at the graphs of y equals 2 to the x, 3 to the x, and 4 to the x. See if you can determine the domain, range, and y-intercept for each of these functions. So the graph of the exponential function y equals a to the x is going to look something like this, with the following features. The domain of the exponential function is from negative infinity to positive infinity. The range of the exponential is from 0 to infinity. The y-intercept is at 0, 1. It is an increasing function. The horizontal asymptote is y is equal to 0. It is continuous, and it is concave up. Now, let's think about how we can use our transformations to create reasonable sketches of more exponential functions. Y equals 3 to the x plus 1 would have a vertical shift up 1, moving my horizontal asymptote to y is equal to 1, my y-intercept to 0, 2, and it would still give me the same shape of the graph. Y equals 3 to the x plus 1 power would have a horizontal shift. It would not change your horizontal asymptote, which would still be at y is equal to 0. However, it does move your intercept left 1, so now it is going to be at negative 1, 1. And our new y-intercept is going to be at 0, 3. Y equals negative 3 to the x. Think about the type of transformation that will occur with this one. The negative on the outside of the function is going to reflect our graph over the x-axis, not adjusting the horizontal asymptote, but rather making our y-intercept at 0, negative 1, and giving us a shape something like this. Y equals 3 to the negative x. Now this is a new one for us. Because the exponential graphs are neither odd nor even, a negative inside the function, like this, will create a reflection over the y-axis. Again, the horizontal asymptote does not change. The intercept is still at 0, 1, but this time, instead of an increasing function, we will see it as a decreasing function. There are many uses of exponential functions in real life. Compound interest, radioactive decay, depreciation, bacteria growth, population growth and decline can all be modeled using exponential functions. The remaining slides will look at some of these basic applications of exponential functions. We will look more in detail with these functions later on in this unit. This is the setup for the compound interest problem you just read. Typing these values in to my graphing calculator, I find that my new balance after 4 years will be $13,500 $23.91. The continuous compound interest model introduces us to a new base, which is base E. E is known as the natural base, or Euler's constant. It is an irrational number similar to pi, and its approximation is 2.718. And an interesting fact about the natural base is that e raised to the I pi power plus 1 will equal 0. Using the continuous compound interest model, we do not have to worry about the number of compoundings. When I type this into my calculator, I find that y, my new balance, is equal to $13,529.96. The initial mass here is 10. To find out how much is present after 80 years, we plug in 80 for T. We find that there will be 1.38 grams of strontium left after 80 years. In many of these equations, you will find the initial amount is this coefficient amount, because when I put 0 in as my variable, which is in the exponent, anything to the 0 power becomes 1. Therefore, this portion will always become 1, and my initial amount is what my coefficient says. To determine the population after 72 hours, we put 72 in for our time and we solve. And we find the population to be about 173 flies after 72 hours.